Hey everyone, this is the People Behind the Science podcast, and I'm your host, Dr. Marie McNeely. Today, in episode 409, you'll be meeting Dr. Teresa Woodruff. Now listeners, if you love stories we share from scientists and you want to continue getting an inside look at the lives and minds of today's researchers, it would be awesome if you could take a moment to check out our Patreon crowdfunding campaign at patreon.com/sciencepodcast. Donations from listeners like you help me keep this show rolling. And in our program today, Teresa is going to share part of her own story. So get ready to meet another one of our phenomenal people behind the science.
Every day, discoveries are made that will change our understanding of the world around us. Dr. Marie McNeely is here to bring you the brilliant minds who are making these discoveries so they can share their incredible stories and take you on an amazing journey. Welcome to People Behind the Science.
Hello, everyone, and welcome to another episode of the People Behind the Science podcast. Today, I am thrilled to introduce you all to Dr. Teresa Woodruff. So, Teresa, thank you so much for joining us today for an interview. How are you?
I'm very well, thank you.
Wonderful. Well, listeners, Teresa is the Thomas J. Watkins Memorial Professor of Obstetrics and Gynecology, Vice Chair of Research in Obstetrics and Gynecology, and Chief of the Division of Reproductive Science and Medicine at Northwestern University Feinberg School of Medicine. She is also Professor of Molecular Biosciences and Biomedical Engineering at Northwestern University. In addition, Teresa is the director of the Center for Reproductive Science, founder and director of the Women's Health Research Institute, and director of the Oncofertility Consortium. She completed her undergraduate studies at Olivet Nazarene University and received her PhD in biochemistry from Northwestern University. Afterwards, Teresa completed a postdoctoral fellowship at Genentech Incorporated. Teresa has received many awards and honors in her career, and she has been awarded the Society for Endocrinology Transatlantic Medal, the Journal of Women's Health Award for Outstanding Achievement in Women's Health Research, a Guggenheim Fellowship, the American Women in Science Innovator Award, the American Medical Women Association Gender Equity Award, the Speaking of Women's Health Distinguished Service Award, the Endocrine Society Outstanding Leadership in Endocrinology Award, the Endocrine Society's Richard E. Weitzman Memorial Award, the Women in Science Award from the Weitzman Institute, the Beacon Award from Frontiers in Reproduction, the U.S. Presidential Award for Excellence in Science Mentoring, and in 2013, she was named in Time Magazine's Most Influential Persons list. In addition, Teresa has received the Distinguished Teaching, Faculty Mentor of the Year, Distinguished Woman in Medicine and Science, Alumni Association Merit, and Distinguished Alumni Awards from Northwestern University. She is an elected member of the Economic Club of Chicago and an elected fellow of the American Association for the Advancement of Science. Teresa was also recently elected to the College of Fellows at the American Institute for Medical and Biological Engineering. And listeners, Teresa is here with us today to tell us all about her life and science. So Teresa, we want to know you both as a scientist and also as a person. Can you start by telling us how you like to spend your time when you're not doing science?
Well, I'm a former cellist, so I like to go to the symphony. Chicago Symphony is one of my favorite orchestras in the world, and I'm a big symphony fan. I'm also a Chicago Cub fan, which this year is a little bit difficult. Last year was fantastic.
Gotcha.
And then I love to cook. So those are the three things that I love to do outside the lab.
Oh, that's wonderful. When did you start playing cello?
When I was 7 years old, actually.
Oh, wow. Do you still pick it up every now and then?
No, actually, I guess about 15 years ago, Yo-Yo Ma came to Northwestern and his niece was in my laboratory and she invited me to meet him. He was one of my heroes. And so I did at intermission and he asked me to play something on his Stradivarius. And
oh, wow.
Once I did that, it was kind of a drop the mic moment. And my nephew now plays my cello and I think that's a good thing.
Mm-hmm, mm-hmm. Well, you have to maybe quit while you're at the top, I suppose.
Right. I think that's it.
Well, that is fantastic, Teresa. Great to get a window into your life outside of science. But I do want to talk about your amazing research next. So can you tell us how you describe your work to someone who's not familiar with your field?
I'm interested in how the ovary works, how the female reproductive cycle works. We all know that the reproductive cycle is about a month in length, but it begins at about the time of puberty and ends at menopause. And the ovary contains all of the germ cells, the oocytes that we'll have for our entire reproductive lifespan. And so understanding how each one of those follicles makes the decision to be part of a reproductive cycle when a woman is 19 and it's May versus one that might sit right next to it and not begin that process for 10 or 20 years is really a biological mystery. So we're really interested in solving that problem. And along the way, we're doing a lot of other work within reproductive science, but understanding the female reproductive cycle is really fundamentally what we're interested in doing.
Wonderful. I love the term you used, biological mysteries. So I look forward to chatting more about your work as we go through our conversation today, Teresa. But I do want to know what motivates you. I talk to so many different scientists who have so many different motivational forces in their lives. Do you have your own force or quote or saying that really keeps you going in every day?
I think as scientists, we're curious. So people who are really curious about how things work around you is someone that I think makes a good scientist. So I think there are a lot of citizen scientists out there that are curious about how the world works. And when we are 3 or 4 years old, we're curious about what makes clouds. And so I think we're all fundamentally driven to ask questions. And for me, then I continue to ask questions over time, and I have been able to make that my life's work. That's been one of the things that's been really exciting for me.
Absolutely. So do you get to work with kids at all and maybe reconnect with that childlike curiosity?
Yes, we have a whole program in our group that is what I call Education and Reproductive Science from K to Gray. And so we have new animations that we've done that are really catchy songs for puberty, reproductive anatomy, and the menstrual cycle. And this is for 8 to 12-year-olds. We have a coloring book for kids younger than that with Olivia the ovary and Timothy the testis. And then we have a number of educational materials for older ages. And one of the issues is really that reproductive science and reproductive health isn't something we think or talk about. And even in middle school and junior high, when teachers are talking about sex, they're really talking about having sex or not having sex. And I think more importantly, we need to understand about our own reproductive health. So those parents who want to talk with their kids are just as uninformed about their own reproductive cycles, or maybe are a little bit skittish talking about how the menstrual cycle works. Mm-hmm. So it's my mission to really, from the earliest stage possible, provide as much information as we can. The puberty animation that I have on our website, and I'll give that information to you later, has such a catchy tune. It's meant to be like, if you remember, How a Bill Became a Law.
Oh, yeah. Schoolhouse Rocks, yeah.
Such a catchy tune. Once you listen to it, you just keep it in your head. And that's what we wanted to do, to make sure that the kids have the terms they need, because maybe they're interested in their own reproductive health. But if you Google comparative anatomy or a question, you might get to a very unsavory part of the web. Mm-hmm. And so we're trying to make sure that from the earliest age possible, kids and adults have access to authoritative information in this field.
Well, I love to hear, Teresa, that you are making this field of reproductive science accessible to wide audiences. And I love the tagline, K to Gray. I think that it's fantastic. So now, can you take us back to the beginning and talk about what first got you interested in science and maybe in particular this field?
I actually came to Northwestern as a graduate student, interested in, again, fundamentally understanding how we get to the answers in the back of the book. So I like science from an early age. My mom talks about when I was in kindergarten dissecting earthworms to try and figure out how their internal body parts work. Mm-hmm. And I've just always been curious about the world around me. So going through college, I really was interested in, again, how people identify the answers in the back of the book, not just the questions, but how do you derive those answers? So I became inspired to do science in college and went to Caltech for a summer experience and really began to be mesmerized by how you ask questions and then can address those questions with a series of experiments that ultimately lead to answers that ultimately go in the back of the book. And so I went to graduate school interested originally in RNA, the kind of nucleic acid we know about DNA that makes up the double helix, and that double helix creates messages called RNA. Mm-hmm. And those regulatory RNAs were of real interest in the mid-'80s. Molecular biology was just starting where we could clone genes. So I went to graduate school at that time of really heady new discoveries that were being made. The genome hadn't even been thought to be sequenced. Then 7 or 8 years later, the entire genome was sequenced. So I have always been interested in science. And when I got to graduate school, I had not thought at all about reproductive science, but was introduced to the laboratory of Dr. Kelly Mayo, who was interested in gene regulation. And I selected the ovary as the vehicle for my study. And once you see how well orchestrated the ovarian follicles are, and the follicle is the fundamental unit of the ovary, it contains a single egg and surrounding cells that make estradiol, and they get metered out over time. So most of them sit in an ovarian reserve that are waiting their turn, and others are being moved into this process of growth towards ovulation each month. And I just became completely fascinated by how that process worked, and also realized that we knew practically nothing about it. So that's kind of my origin story. And then a high affinity interaction occurred between myself and reproductive science.
Well, it's great to hear more about your path. And now you mentioned that working with Kelly Mayo in graduate school was sort of the gateway to your current field. And I love hearing about other inspirational figures or people who may have had a big impact on your career path as a scientist. So are there any other people who stick out in your mind as role models or these impactful figures?
Kelly Mayo certainly is one of my role models, someone I've always patterned myself after, and he's always been an inspiration to me and has always given me best advice along the way. Nina Schwartz was also a Northwestern pioneer in reproductive science and came up in the sciences in the 60s and 70s and really taught me how to think in a very quantitative way, not just qualitative. How could we kind of describe an event, but how could we really quantify the events? And we celebrated her 90th birthday last year, and she's always been a real mentor to me. And the two of them, I think, form the two pillars of my career.
Now, is she still doing science at 90?
Nope, she's not doing science.
She's retired.
Still gives advice.
Gotcha.
Always important advice that I like to take advantage of.
That is wonderful. Well, Teresa, like I said, great to hear more about your origin story, where you came from and how you got to where you are today. But I do want to chat now about some of the work you have going on in the lab. I know you've got lots of projects going on, but is there one in particular that you want to tell us about in a little bit more detail today?
I think one of them that I'm particularly excited is that we've been able to 3D print an ovary. Mm-hmm. We've been interested for some years in trying to provide fertility option to young cancer patients. And about 10 years ago, it would be true to say that almost no young female cancer patients who are being treated with life-preserving cancer therapeutics, but also fertility-threatening chemotherapeutics or radiation treatment, would have a discussion about their ovarian function. They might be told that they would get sick or nauseous, they might lose their hair, but they wouldn't be told that at the end of the day, they might lose their fertility or, in fact, be sterilized at a young age. At the same time, men were being offered fertility options, which would include banking semen. Females with the same hope for surviving that the males had, they weren't being offered the same options. And so I coined the term oncofertility to try and develop a series of options for young cancer patients, both ways to protect and preserve ovarian function, as well as to really develop corridors of communication between oncologists and fertility specialists so that patients could take advantage of even existing options like IVF when time was available between that first diagnosis and the first sterilizing treatment. So we've developed a number of technologies over the last 10 years that have provided new options, new hope for cancer patients. And just last month, we published the first 3D printed ovary that we transplanted back into sterilized prepubertal mice. And we were able to get live birth from those transplants. This represents really the hope for the future for our cancer patients, and particularly for the pediatric cancer patients that are unable to go through puberty because of that loss of reproductive function, of ovarian function. So we're really excited about this technology and are now translating it to the next level, which is actually the mini pig, together with my former student and now colleague here at Lurie Children's, Monica Laranda, and hopefully moving to humans within the next 4 to 5 years.
Well, Teresa, this is a truly remarkable project and a phenomenal accomplishment in science, I must say. I know a lot of our listeners out there might be familiar with 3D printing with the little plastics and things. Can you talk a little bit about what materials you use to 3D print these ovaries?
Yeah, we're using a 3D printing kind of in the same way as you said, hobbyists actually use 3D printers to print widgets and glassware and parts for model airplanes. Mm-hmm. We're using, our material is not plastic, our material is a biological ink. And that biological ink is gelatin. And we've also developed methods for printing the extracellular matrix from the ovary. And this is in collaboration with a terrific biomedical engineer whose name is Ramil Shah and her group. they've been developing a number of different inks. They've been able to print bone, they've been able to print trachea, and this collaboration with us is the first to really develop a soft organ 3D printed mimic, and it's functional, as I said, giving rise to both the endocrine hormones as well as live birth. So that's a pretty high barrier for an internal organ to be able to support development all the way to fertilization, implantation, and live birth. So we're really excited not only for the reproductive field, but this, I think, opens up options for many other soft organs, liver, kidney, other organs where we urgently need options for transplant patients.
Oh, absolutely. Now, are there challenges associated with kind of scaling up in terms of the 3D structure, being able to support itself when you're moving from a mouse then all the way up to a human?
Well, I think that there will be some challenges, but not insurmountable, because the materials we're using are the same kind of materials that organs themselves use to build basically the skeleton of a soft organ. So each of those challenges, as we meet them, will come up with strategies that mimic what the ovary itself does. And in fact, in order to just supply either a gamete or a short-term amount of hormones, we really wouldn't need to replace an entire tissue. We would just replace part of that tissue for the amount of time necessary to give the function that that individual needed.
Sure. Well, Teresa, phenomenal to hear about this project. And you sort of touched on a little bit how you address challenges. And I love your term, nothing is insurmountable there. But I do love talking about some of the challenges that scientists face, because I think it's really important to share these stories, because oftentimes the public, the listeners out there, might only hear the success stories, and they may not realize all the challenges, the struggles, the failures that scientists have before those success stories come out. So, Teresa, do you have a story of one of your own challenges or a really big failure that you had and how you worked your way through it?
Oh, we also just published about a month ago a paper on what's been dubbed menstrual cycle in a dish. It's a 30-day cycle that we've been able to use a microfluidic system, another engineered way to study the reproductive system. And we're able to connect basically an ovary from a mouse together with a human fallopian tube, human uterus, human cervix, and a liver for metabolism in a little circuit, which is much like what we have in our own bodies. Basically, each of our organs are connected by microfluidics, basically the blood vessels that move nutrients to the organs and then waste away from the organs. So we developed this system, and I'm now convinced that microfluidics are the future of biology, because if you think about the way all of biology is done today, it's in a petri dish, and basically in static culture, the cells are just bathed in their own metabolic waste. So we're really studying the signaling pathways of waste byproducts. And so microfluidics, just like our own biology, allows for the constant replenishment of nutrients and removal of that waste. So that paper was published this last year, but really that one paper is the culmination of over 5 years of work.
Oh, wow.
And there were many times during that 5 years, because basically we were building the ship as we were trying to float out of the harbor. Mm-hmm. Again, was a collaboration with a group of engineers at Draper Laboratories in Cambridge, Massachusetts, who had the kind of technology that company actually has built many of the parts of the space shuttle, for example. So they were great engineers, and we had to iterate back and forth in order to make a prototype system that they had really work fundamentally like we needed it in a biological setting. And there were many setbacks. We would get a system and it wouldn't quite work, and we'd have to iterate back and forth. And so over those 5 years, I think there were many times where members of the team might have thought, well, this is just not going to work. It's not going to actually end up in being the product we're interested in. And in fact, that was always a possibility. I think science is not about proving something. It's about discovering things. It's not that you believe something. It's that you test something. I often reminded our team that the endpoint wasn't to show something. It was to test something. And that's oftentimes the best way to think about going through the times, and in this case, years, where a very large team was continuing to make the slow and steady progress, but not the ordinary output that you see in science today. So because of the way grants are funded, you have to have a lot of productivity during basically a 5-year time frame, which is the time of the grant. And if you're not able to make the progress, then you're not able to actually continue the work over the next period of time. It's often thought that it's a failure if you're not able to make these intermediate kinds of publications. I felt that if we could continue to iterate with the engineers and really ask questions of each of our content experts, so each of our organs had content experts. The ovary was run by a former student of mine that's now at University of South Carolina, Dr. Shuo Shuo. So he was responsible for trying to get the ovary to actually make all the menstrual cycle hormones over a 30-day period. Dr. Julie Kim was the director of our uterine project. Can we get the uterus to expand to respond to estradiol and progesterone the way they do in vivo? Dr. Joanna Burdett at University of Illinois, Chicago had the fallopian tube project, and she was trying to see if the cilia would beat. And the cilia in the fallopian tube is what moves the oocyte down from the ovary to the uterus and where fertilization takes place. It's also where ovarian cancer arises. And so being able to culture these tissues for more than 30 days in culture with the function that we knew they had in vivo but had never been recapitulated in flat plastic was as difficult as building an entirely new platform, an entirely new way of doing biology, which is this microfluidic system. So we were ultimately able to build the system, and we called it EVATAR. That's kind of a play on the word for avatars that people know about.
Yeah.
The avatars are the mimics of the person in virtual space. So the EVATAR is basically the mimic of the reproductive system in a active, functional 30-day system. So that really was a struggle. At many points, we touched the bottom and had to keep clawing our way up and keep realizing that the body does this. The body is actually our best model. And instead of mimicking a petri dish, could we better model the way the reproductive tract interacts? And ultimately, we were able to do that.
That is wonderful. And you mentioned that there were maybe murmurs from people in the team who were starting to think this isn't going to work at different points during this 5-year span. Was there ever a point where you find yourself really having to be the cheerleader to keep it going? Or was there a point where you decided we need to make this work?
Yeah, I think at many points you kind of wonder if it's going to work. And in fact, one of the things that we have to appreciate in science is that we're batters, not pitchers. Going back to the Chicago Cubs that I love, to use a baseball analogy, basically in science, you're making a hypothesis. And if you're really doing it correctly, since we really don't know the outcomes of these studies, and again, if you're not trying to prove something, if you're just trying to test, about half the time you're actually proven correct, and the other half of the time you're proven not correct. And so a pitcher has to succeed at least 90% of the time, and batters basically have to succeed about, on average, 1 out of every 3 times. So we're more like the batter than we are the pitcher, and still can be professional scientists, professional baseball players in the analogy. And what many young scientists don't realize is that the null, the opposite to what your hypothesis might have stated, some people think that's a failure, that's not success. To me, that is part of the richness of science, that when we get something that we didn't expect or that was incorrect, that simply informs what we can do next. And I think if there's one thing I could do to improve science in the long term, it would be to find a way that we could all describe the negative data in as much depth as we do what the positive data is. And the reason I think that would be important is a lot of people will go down similar paths. And if there's no literature that reflects on a graduate student's 3 years of work that resulted in the null answer, then we lose out on the richness of that data. It is not better to be right or wrong, if you will, when you're analyzing the outcome of your hypothesis. Both are equally valuable. And that's something that I think we need to do better as a scientific discipline.
Absolutely. And I think it just increases efficiency and makes resource use more efficient in terms of not having people repeat the same things that everyone knows doesn't work, but it's not been published. So
Right. A lot of times people find that when they go to meetings, and all of our society meetings are important because the posters are often, and the poster conversations are often where you get that information. But many students haven't been to meetings for many years. And I encourage all my students to go to meetings, get to meet the people in our field, as well as to learn what's been tried, which often comes out in these posters.
Absolutely. Well, Teresa, we don't just want to focus on the difficult times, although this story did have a happy ending, but I do want you to share another success story with us, because I love celebrating success in science in all of its forms. And these can be big wins or even small victories that just meant a lot to you.
Well, I think the 3D printed ovary and the microfluidics in a dish, the Evitar, those are really great outcomes. But I think the thing I'm really most proud of is that 10 years after I coined the term oncofertility, we really have a field of medicine that didn't exist before. We have young women who formerly would have been sterilized and wouldn't have even known it by their cancer treatment, now having options and cryopreserving their ovarian tissue or eggs or embryos. So now, again, having that same hope for survival because of the great advances we have in cancer treatment, also paralleled with their ability to maintain their fertility. So to me, that's been one of the things I've been most not only proud of, but humbled by, to have been part of this large field of oncofertility that now is really global, to be able to hold the babies of some of these young women and see their lives move back from what is an extraordinary existential crisis, which is that cancer diagnosis, back to health and back to the fullness and richness of what they hoped for before that cancer diagnosis. And that includes having children of their own. So that's something that I'm very proud of.
Well, congratulations, Teresa, on this wonderful success, and definitely developing this field, as you're mentioning here, has had a big impact directly on people's lives. And I absolutely love those stories. And I know we've chatted about some different aspects of your career. And I think as a scientist, it's easy to get kind of sucked into the research and spend a lot of your time reading the literature, spending a lot of time in the lab. But we love talking about books on this show as a way to maybe escape from science for a little while. And I'm always adding books to my own reading list. So Teresa, do you have a book recommendation for us today that I can add to our website for our listeners?
I would read The Ovary of Eve, even though it sounds like my own field. It's a fantastic book. It's Clara Pinto Correa, who's a great historian. And she talks about how the world came to understand the egg and the sperm. And really, it wasn't until the 18th century that there was even an inkling of an understanding of how conception works. And the homunculus was one of these kinds of weird turns where social science, or just what we expected there might be in a sperm, with the image of a man with his beard and hat preformed. Mm-hmm. All of those kinds of things, which were informed by religion and social expectation, male dominance, etc., really comes into a full and in some ways hilarious light with this book. And so I think that is really just a fantastic read for non-scientists and scientists. My mom's read it. She loves it. I think it's just a terrific book.
Perfect. And that was Ovary of Eve?
The Ovary of Eve.
The Ovary of Eve. Listeners, add this to your reading list as well. And thanks for this recommendation, Teresa. And I know we've talked about some of the different places that you've gone as a scientist for your training. And I think travel is a big part of the life of a scientist in terms of sharing your research, going to conferences, working with different collaborators. So do you have a favorite place, Teresa, that science has taken you?
One of my first trips was actually to China, and I went to Peking University in 1991, and you'll remember that was a time just after some unrest within Beijing. Mm-hmm. But I was there to teach reproductive science and some molecular biology techniques, and I had some wonderful hosts, which were some of the students that were in the class. In particular, I remember taking a bicycle at that time around the city of Beijing, and I hadn't been on a bicycle in some time before getting there. And the night arriving at midnight and then getting to the place I was staying was actually the Russian embassy of all places. And so I think what they told me that night, as I was pretty jet lagged, was that there would be a bicycle out front and for me to ride to the Hewlett-Packard plant and take a left. And then I would see Peking University. And when I woke up the next morning, kind of befuddled at even what time it was, I couldn't imagine riding my bike to the Hewlett-Packard plant, even imagining what the characters would look like. But I quickly set out among the hundreds of thousands of bicyclists at that time. And when I saw the image of the characters of Hewlett-Packard, it was my happiest moments in all of life, let alone science. And then had to turn left across the traffic, which was equally interesting. And there was a moment where someone noticed that I was standing there looking to see how I would get across. And it was as if Moses was parting the Red Sea when people started stopping. And then I was able to go across. And it was a really great experience. And I was just back in Beijing this last December, actually. And the city has changed a great deal, but the science is still strong. The training is still very active. There are very few bicycles now, comparatively. That was one of the great memories I have of traveling for science.
That sounds a little bit like a harrowing experience, I think, Teresa. I'm not great on a bicycle either, so I don't know if I would have made it.
Yeah, it was a lot of fun.
So now, were you able to take some time to explore Beijing at all, or was it mostly of focused? Okay.
Yes, I was. In both cases, I went up to the Great Wall that first time. And at the time in 1991, there was almost no one who was up on the Great Wall. And so I had the place to myself with the students who were accompanying me. At one point, we walked quite a distance. And I sat down and they gave me a Coca-Cola. So there's a great picture of me sitting on the Great Wall with a Coke in my hand. And it's one of my great images of that time.
Oh, that is fantastic. Well, Teresa, great to hear about one of these momentous travel experiences for you relatively early in your career. And you mentioned some of the students that accompanied you on this trip and some of the colleagues that you've been working with over the years. And I think the people are part of what makes science so wonderful. And I know there are stereotypes out there about what scientists are like, but many of the people that I've worked with are funny, creative, and amazing. So we love sharing stories on our show about some of the quirky traditions and fun memories and hilarious things that scientists do when they're together. So do you have a story of your own that you can share with us today?
Well, we have a Velvet Elvis in the lab.
Ooh.
So one of my students gave me a Velvet Elvis. I think she came back from her home, which was in Alabama, and she brought that, and we hung it in the lab, and I thought, it looked at me for quite a while, and then I realized that if we touched the belt of Velvet Elvis with every grant, we would actually get funded. That was at least the way I posited it. And so we touched every grant to the Velvet Elvis when we started, and that was when we had paper grants. Now that we have electronic grants, someone has to take some part of that grant, touch the belt of Velvet Elvis. And I think the laboratory now loves that, and probably it's one of the most quirky things we do in the lab, but it's a long-standing and good tradition. I think the other tradition we have is of the graduate students as they leave. We have a picture of the graduate student, a frame together with an image of their first paper published. So the current laboratory graduate students are able to look up literally around them and see those individuals who have gone before them. And they know the names because of their science, but they also know their faces. And then when they come back, they can meet them. And finally, when people leave the lab, we all sign the bill of Northwestern baseball cap right under the bill. And as people leave, we're able to give them a picture of the lab at the time they're leaving. But also, I think the most important thing is this baseball cap. And I always say that no matter where you go and whether there are ups or downs, you can always look up and there we will be looking down on you. So that's a very kind of cherished memory for me as I give these hats out, and I think they're well loved by a lot of folks.
Oh, well, I love these traditions you've described. I will admit that you are the only one I've met who has a Velvet Elvis. So
yeah, I think that's very true.
That is a claim to fame there. So how big is this?
It's a full size, life size.
Oh, wow.
So yeah, it's pretty big.
Yeah. Wonderful lab decoration. I like it.
Yeah.
Well, Teresa, it's great to have fun with the people in your lab, but it's also wonderful to chat about these big questions. And I know you are tackling some of them in your lab today. And I'm sure there are things standing in your way from doing everything you'd like, things like funding, staff, technology, feasibility. But Teresa, if I took away all of those restrictions today, what is the one question you would want to answer?
I want to answer how follicles make decisions. Sounds rather anthropomorphic to ask how they make decisions, but in women, we have 1 million follicles that are made and are available within the ovary at birth. And they are metered out until 51 and a half years, which is the global average for menopause. So we often worry about the fact that the egg quality is lower at 37 than it is at 27. But I think the remarkable thing is we even get to 37 because ordinarily these cells would all develop. So something is maintaining them in this dormant but available state, and then one follicle is given the signal or some repressor is removed and it moves into this growing population. And we really don't understand how that works. That's really what I want to try and solve. And part of it isn't just money, part of it is intellect. We haven't yet figured out how to target, how to figure out this problem. So we continue to develop tools and move closer and closer to trying to solve that particular issue. And building the 3D printed ovaries, having the Evitar available are all tools that hopefully one day will help solve this particular issue.
Absolutely. Well, this is a phenomenal question to be working towards answering. And I know we talked about different aspects of your career throughout our conversation today, Teresa, but I do love to leave our listeners with advice. So is there one piece of advice that really helped you on your journey that you can pass on to them today?
I think that in the science, the wings of success really are resilience, vision, and confidence. And I try and tell my students that all the time, that resilience and vision and confidence are the ways that you will stay the course in a long and healthy career. And The equal balance to those wings of success really are the triple threats of our profession, which are ego, paranoia, and worry. And sometimes if we are too egotistical, or if we become paranoid and think someone is thinking something about us when they probably aren't, or if we're just really generally worrying, those can be the anchors that keep us from soaring. So I think if we can balance and remember that resilience is important, having a vision of yourself and where you want to be, and having the confidence to do that without having ego or worrying about what someone else might think or worrying just generically. That's my TK-ism for success.
Ah, fantastic. So is there any other last piece of advice, Teresa, or a last note of inspiration you want to leave our listeners with?
I think for many people, it's really a matter of just starting, just getting going. And sometimes we sit and think too long. And science is really a physical sport. It's not just how you think, it's actually what you do. Getting up out of your lab chair and going to actually culture cells and doing work, it is the only place that you can make discoveries. So just start is the best aphorism I can give people.
Well, that is excellent advice. Listeners, get moving. The wonderful note for us to end our conversation on, Teresa. Can you tell our listeners, if they want to learn more about you and your work, where should they go?
They can find all of our work at woodrufflab.org. That's the website for the Woodruff Lab, and they'll find information on our research on oncofertility, some of the educational work like the Reproutopia, some of the policy studies we do, et cetera. So that's the best place that they can find us.
Perfect. Well, listeners, I've been to Teresa's website. I know it is wonderful, so definitely check it out. Learn more about her amazing work. And Teresa, thank you so much for joining me today and sharing a piece of your story.
Thank you so much.
It was a pleasure to chat with you, and listeners, wonderful to have you with us as well. We'll see you next time on another episode of People Behind the Science. Your voyage to explore the lives of today's exceptional scientists has just begun. You can find everything we talked about today, including our guests' favorite books, biographies, photos, and more, when you visit us at www.peoplebehindthescience.com. I look forward to chatting with you next time on People Behind the Science.